right, so here's the example, a materials property example where we're going to use Hooke's law and Poisson's ratio. So if you remember, Hooke's law is how we relate stress and strain using the elastic modulus. So when we're in the linear region of the graph, the elastic modulus E equals the normal stress sigma over the normal strain epsilon. And then Poisson's ratio, funny V or nu, someone pointed out, equals the strain in the lateral direction divided by the strain in the longitudinal direction. So the fact that this problem tells you that it's using Hooke's law and Poisson's ratio is kind of cheating, but that's okay. It's good to know what we're doing. Okay, so now this problem. We talked about how cool this problem is. We have a nylon that has an elastic modulus. So I'm going to start as I read this problem writing my givens. So I have E of the nylon equals 360 KSI. I have the Poisson's ratio of the nylon is 0.4. And that's rod 1. So that's the inside of this two material system. And it has a diameter D1 equal to 2.5 inches. And it's inside the steel. So the elastic modulus of the steel is 29,000 KSI. Side note, elastic modulus of steel, 29,000. Elastic modulus of the nylon, only 360. So nylon is a lot squishier. It's a lot less stiff. So it has a much lower elastic modulus than the elastic modulus of the steel. Okay. So, and then we have a Poisson's ratio for the steel equal to 0.29. And that's tube 2, so that's the outside of this thing. And the inside diameter of the tube, we have D2 equals 2.52 inches. So, what's going to happen here is we have this external load P is going to be applied to the nylon rod, compressing it. When we compress things, we make them shorter, which means that they're going to get fatter. So they're going to get shorter in the longitudinal direction and fatter in the lateral direction. And we're supposed to figure out at what value of P, so what is this P, will we close this gap? Will this space between the nylon and steel be closed? Okay, so we talked about how the nylon is what's going to change size. The inside is going to go from 2.5 inches to 2.52 inches. It's going to close this gap and it's going to fill that hole. So, what can we calculate from our givens to start with? So we have elastic moduli and Poisson's ratio, but so far, as elastic modulus goes, we don't have a stress, we don't have a strain yet. If we look at Poisson's ratio, there's a lateral strain, a longitudinal strain. And if we think about this, we have the diameter is going to change from 2.5 to 2.52. That's in the lateral direction. So we can calculate a lateral strain by using this change in diameter. Okay, so that's the first thing we can calculate, is we're going to calculate, oh yeah, I forgot to write what we're supposed to find P to close Okay, so the first thing we're going to do is calculate lateral strain to close the gap. Okay, so strain, whether it's lateral or longitudinal, equals delta over L. Since we're looking at a lateral strain, we're going to have strain lateral equals the change in diameter all over the original diameter. Okay, so that equals the change in diameter is 2.52 inches minus 2.5 inches, all divided by the original diameter of 2.5 inches. So we get a lateral strain equal to 0.008 inches per inch. Okay, so now we have a lateral strain. So now we have this. Well, if we have that, we can calculate, and we know the Poisson's ratio, we could calculate the longitudinal strain. So we need the Poisson's ratio of the nylon because that's the material that is changing right now. The steel, we don't actually need to know anything about the steel because we're not doing anything to the steel. We're only doing stuff to the nylon. Okay, so now we're going to calculate the longitudinal strain using Poisson's ratio. So Poisson's ratio equals funny V. It's technically a negative, but we're not going to worry about that. Lateral strain, that's going to get fatter, so that would be positive. The longitudinal strain, it's going to get shorter, so that would be negative. But Poisson's ratio equals lateral strain over longitudinal strain. So we need to have, and this is using V of the nylon, so the Poisson's ratio of the nylon equals 0.4. So we do 0.4 equals the lateral strain, this, so that would be 0.008 inches per inch, all divided by the longitudinal strain, and we get a longitudinal strain equal to negative, well, we knew it was 0.02 inches per inch. All right, so the reason why we need the longitudinal strain is because we're squishing this in the longitudinal direction. So now that we know the longitudinal strain, we can use Hooke's law because now we know this strain. We know E, we're going to use E of the nylon, and we can calculate the stress. And then the stress we can use to calculate P. Okay, so now we're going to calculate the stress in the nylon using Hooke's law. Okay, so Hooke's law is E equals stress over strain. And we're looking in the longitudinal direction, and we're looking at the nylon. So E of the nylon equals 360 KSI. Okay, and then we're going to plug this longitudinal strain into there. And then we can solve for sigma. So sigma equals E, big E, 360 KSI times negative 0.02 inches per inch. So the stress will also be in compression. It will equal negative 7.2 KSI. Okay, so we're getting so close. Now we can calculate P using the stress equation, which is just normal stress, sigma, equals the force over the area. And here, F equals P. So, P equals sigma times the area. So this equals negative 7.2 KSI times the area is pi over 4 times the original diameter, 2.5 inches squared. So this is all the area. And we get that P equals 35.3 kips. And it's compressing it. Pretty awesome problem. So we went from a lateral change in diameter to be able to calculate the longitudinal force causing that lateral change. So I think it's awesome.